Welcome to Unit 5 of this course. In the last unit, we saw what are called regular properties. In this unit, we will be looking at what are called omega regular properties. This symbol stands for the Greek letter omega. In this module, I will do a short recap of the tools to describe properties. I will conclude with an overview of what we would be seeing in this unit. We have been looking at code as transition systems. So this is a transition system. Additionally, in order to be talking about properties of this transition system, we defined what are called atomic propositions. Here, there are two atomic propositions P1 and P2. Once we have them, we label the states with the sets of atomic propositions that are true in that state. For example, here P1 is true, here P1 and P2 are true, here P2 is only true, and here none of them is true. Once we have this model with us, we can talk about what are called traces. Let us look at executions of this transition system. For example, looping, this is an initial state. Looping in this state forever is one possible execution of the transition system. Take that execution and look at the label of each state in that execution. That will give us what we call a trace. So this trace corresponds to the execution which just stays in this state. What about this? This corresponds to the execution that starts from this initial state, goes to this state and keeps looping here forever. What about this one? It starts here, goes here, then takes this transition to come here, and then goes back here and keeps doing this loop, and this is the trace corresponding to this execution, and so on. So given a transition system like this, along with the labels, we can talk about traces. Here is a more formal explanation. Let AP be the set of atomic propositions. Given this set AP, we look at the power set of AP. So the power set is the standard thing that you know. It looks at all subsets of AP, starting with the empty, singletons, and then P1, P2, P1, P3, and so on, till the set consisting of all of them. This is the standard power set. The trace of an execution is an infinite word. Here I have emphasized the infinite word over power set AP. So each trace is an infinite word over the alphabet power set AP. So if you consider this to be our finite alphabet, each trace is a word over that alphabet. And given a transition system, we can talk about traces of a transition system. We look at each execution and then take the corresponding trace, and the set of such traces is denoted as traces of TS. This is something which we have seen already. The point that you need to note is that this is our alphabet and these are all words over the alphabet. Now let us come to property. So far we have been looking only at the model. Considering this to be our alphabet, we denote APinf to be the set of all possible infinite words. Now what is a property? For example, the property which says P1 should always be true will give us the set of all infinite words where in each letter P1 should be true. There could be other things true as well, but P1 should necessarily be true in each letter. Let us look at another example. P1 is true at least once and P2 is always true. So this will give us another set of words where P2 is always true and then P1 should be true somewhere. The point to note is that a property over a set of atomic propositions is a subset of AP-inf. What is AP-inf? It's the set of all words over this alphabet, and a property is just a set of such words. Here is where we are. Given atomic propositions, we have this transition system, and then somehow we describe a property, and we say that the transition system satisfies the property if all its traces are contained in this set. Now the question is, how do we describe this set? We have seen ways of describing this set using the operators G, F, X, GF, and in the last unit we have been seeing what are called finite automata, and finite automata can help us specify safety properties. And how do they do that? They describe the set of bad prefixes, and the property is just the words which avoid these bad prefixes. In this unit, we will be looking at something more general called omega regular expressions. We will be using omega regular expressions to specify properties like this. There are two goals. The first thing, we would use omega regular expressions to specify properties. So in the next module, I will define what omega regular expressions are, and I will give a lot of examples to make it clear. Once we do that, what we want is an algorithm to check this. Suppose I give an omega regular expression and this transition system. How does one check, or what is an algorithm that checks if the set of all traces is contained inside this omega regular expression? Note that the set of all traces is infinite, and the set of all words belonging to this property is also infinite, could potentially be infinite. However, the descriptions are finite. Using these finite descriptions, we want to give an algorithm that checks if all traces of this transition system satisfy the property given by this omega regular expression. In this unit, we would not be able to complete the second point. However, we would give some necessary mathematical objects that will help us describe an algorithm in the next unit. This is the broad overview of what we have seen and what we will be seeing in this unit. You can now jump to the next module.